Evening, guys. This is a question from the Semester 1, Extension 1 Barker past paper from 2012, and it's a question that incorporates, it's a simple question, but because it incorporates so many different concepts just in small amounts, it's going to take me a while to explain, but it's very, very important and uses some really core ideas in lots of different questions. So it's definitely worth your while. It's question 8, so it says, by considering the sketches of y equals sine of 2 theta, so there's a little 2 theta in there, it's cheeky, changes things a bit, and y equals cos of theta, or otherwise, determine how many solutions this equation has, sine of 2 theta equals cos of theta. So whether they've just equated those two in the domain of between 0 and 2 pi. So I've just drawn that little domain up here. And of course, you've probably come across this idea before, but when you've got simultaneous equations and we've got this one function here, sine of 2 theta, helps when the pen's on, when you've got sine of 2 theta and equals cos of theta, what you can do is you can draw the graph of one of them, y equals sine of 2 theta, and the graph of y equals cos of theta, and where they intersect, those points of intersection, graphically, they're the solutions. So what we're going to do is that the general philosophy we're going to use is we're going to graph these two functions. So I'm going to do sine of 2 theta in green and cos of theta in blue, and then just count how many times they intersect, basically. So that's all we're going to do. So what we're going to do is, we'll start off with cos, because cos is the easiest one. We've been doing it since Jesus was a boy. So what we do is I've drawn this little unit circle over here. Now you might use a calculator, you might just chuck in numbers in, but this unit circle is definitely something that it has been useful for me. So I'll just briefly explain it, and its use is to, when you've got cos or sine, when you want to know what cos of 90 is, or cos of 180, or cos of 270, or you want to know what sine of 90, or sine of 0, or anything like that, that's when this circle comes in handy. So it's called the unit circle because it's a circle of radius 1 unit. And I've just drawn this little triangle here. So this is the little radius and a little right angle triangle. And you can see that I've drawn here that the height y is sine theta and the length x is cos theta. And you might say, that's weird, what's up with that? So where that's just come from is I've just drawn this little diagram down here. Cos is adjacent over hypotenuse, so x over 1, which is just cos x. So this length here, x, is cos of theta. And sine of theta is opposite over hypotenuse, so the so in Socotoa. So it's y over 1, opposite over hypotenuse, and that's just y. So that's why this x distance here is cos of theta, and this y distance is sine of theta. And where that's useful is, say you want to know what cos of 0 is. So you imagine this angle here is 0, okay? And when it's 0, obviously this 1 will just be lying along this x-axis here. And the x-axis at this point will be 1, the distance of this this projection, because it'll just be straight down. And so that's why cos of 0 is 1. So when we chuck in 0, we're just going to get 1. So I'll just do our little dots as we go. Now let's think about what cos of pi on 2 is, which is this point here, or cos of 90. So we chuck in 90, and you can tell when it's 90, it's just going to be pointing straight up. When it's pointing straight up, there is no x value, because it's just literally straight up in the air. So x will be 0. So at 90, or pi on 2, cos of theta is 0. Now let's imagine cos of 180. So 180 is in here, so it just goes all the way around. This little blue thing, if theta is 180, it'll be all the way around, and our x value will be minus 1. So at cos of pi, we're looking at minus 1. And after a while, you can just kind of see what's going to happen. It's just going to go something like this, because you kind of just get a feel for the shape of things. So where's it going to go back through? So 3 pi and 2, so that's 270 degrees. Cos of theta, it's going to be pointing straight down when you put 270 in here. So you're going to have no x value, so it's going to be 0. So that's where it cuts the x-axis again. Beauty. And then it finally finishes at 2 pi, because 2 pi is just the same thing, of course, as 0. So that's the graph of cos of theta. Now we're just going to do the sine thing, the sine thing. We're going to do the same thing with sine of 2 theta. So all of these, any sine or cos will fluctuate between 1 and minus 1. okay? Unless there's a little number out the front. So if I put a little 2 out the front, that would make the high point 2 and the low point -2. If there was a 6 out the front, it would fluctuate between 6 and -6. So that's what putting a constant out the front does. When you've got a little thing like this, when you're changing the number in front of the theta, so it's 2 theta or a half theta or something, it changes the period, so it bunches up. So instead of being something like this, it might be something like this. Like it fluctuates more if you've got a number greater than 1 out the front. But we'll just quickly look at that. So let's chuck 0 in here. So theta equals 0. So 2 times 0 will be 0. What is sine of 0? So we're looking for the y values nowadays. Now. So when we put this theta equals 0, it's just going to be lying like flat like this. And theta, there's going to be no height. So beautiful. So it goes through 0, 0. Let's chuck pi on 4 in. So when we chuck pi on 4 in, so I'll just do y of pi on 4. So that symbol just means we're putting y of 4 in. Sine of 2 times pi on 4, which is sine of pi on 2. So what is sine of pi on 2? Pi on 2 is 90 degrees. So when we put 90 in here, it'll just be heading straight up. And so the height, which is the y value sine of theta, will be 1. So pi on 4, we're looking at this 1 here. Beautiful. Alright, so a few more. We'll just do one more. So sorry if this is a bit laborious. One more dot, and then we'll just do a quick little fill out. So sine of pi on 2. So we put pi on 2 into here. Pi on 2 right into there. And then we times it by 2. So pi on 2 will just go to sine of pi. So sine of pi is 180. So when we put 180 in here for theta, it's just going to be flat. And then you're going to have no y value. So it'll be 0 there. So you can see what's happening. Sorry, I just leaned away from the mic there. You can see what's going to happen. You kind of get a feel for what these are doing after you've subbed in a few points. So it's going to be something like this. Trying to keep it, because you've got to keep the humps kind of the same kind of size. And once you've got one hump, you can usually just work out what the rest is doing. Beauty. So there's our two graphs. So let's count the amount of times that they intersect. Alright, so it'll intersect once there. That's where we've got an intersection point. It'll intersect once there. We've got another intersection point. Once there, and once there. So we've got 4 intersection points between this domain. So the answer is C. Beautiful. So that's all we've got to do. So we're using, just in summary, we're using the kind of idea that you can draw two functions. And if where they intersect, that's the solutions to the equation, to this equation, in this case sine of 2 theta equals cos of theta, and you could have just chucked these things into a calculator and be like, oh, what's cos of 0, what's cos of pi on 2, but when you're sitting at university in a lecture or something, you're trying to think and you're too lazy to reach into your bag, it is handy, for me anyway, just to remember this little diagram. Okay, beautiful. So hopefully that was clear, and I'll see you in the next one.